Okay, good morning. Okay, let's start the lecture, okay? Another quick reminder, remember next week we're going to have quiz 1. Okay, so I sent an email to everybody. Please join your tutorial section. So before we start the lecture, just want to quickly review one of the assignment questions student asked here. I predict maybe there will be some common problems. So this is the first assignment here. Sorry, this is the first question in the assignment number 2. So this is a question about parameterizing the given curves. Now, it's the number C question, okay, so part C question. It's given a plane and a cylinder, okay, asking for basically the parametric equation intersected by the plane and the cylinder. Okay. Now this question here, I think the first question is, some student wonder, is this a cylinder? Because by the look at it, it's a circle, right? And this is a circle, theoretically, this is a circle in the X and the Z plane. So you should have a circle in the X and the Z plane, right? Yeah. And that circle has a unit radius 1. But in 3D space, okay, so in 2D space it is a circle, but in 3D space you basically extend that circle, right, up and down to infinity. So that will give you basically a cylinder. Okay. So that will give you a cylinder here. Okay. And now you have a plane. I don't know how the plane here. So the plane will go through it and then cut through it. Okay. Then the intersected one here, it's basically give you an ellipse. Okay. And the question asking for the parametric equation of this elliptical circle here. Okay. Yeah. So how do we deal with this kind of question is very similar like the kind of idea in the part A. Okay. If this is the red one is what we're looking for, and the red one must be some kind of curve satisfying both the cylinder and also the plane. So you're trying to get a set of a parametric equation that satisfies both of this plane equation and the cylinder equation. Okay, so that's the point. Now for cylinder, we have learned, basically this is a circle, right? This equation. And we have learned from part B, you can have a parametric equation x equal to radius 1 times cosine omega t. Let's say we'll just use t. And z equal to sine t, right? That's a candidate. That's a candidate for this cylindrical or circle, right? Equation at it here. Now, remember what I said. So this ellipse equation must satisfy both of the plane and the cylinder. So which means, so any one of the points, right, or the coordinates of the point on the red curve must satisfy this and this. So it has to satisfy this one here, which is a circle, and this plane at it here. So then what do? We can simply substitute this x and z back into the plane equation here. Right? So then you sub into the plane equation. Okay? So you can see if you sub this back into the plane equation, x replaces cosine, z will replace sine. So 4 cosine minus y plus sine t equal to 3. Then you solve for the y, right? And so now you have x, y, z, they're all in the function of parameter t format. And that essentially is the parametric equation, because what we did here, we substitute this into the plane here, and then we get expression for the y. So the x, y, z here must satisfy both of the cylinder equation and the plane equation. So that's the answer here. That's basically how you use the substitution idea to obtain this parameterization of a certain curve. Okay? Yeah. Let's continue on a vector function from previous lecture. So this example I didn't finish at the end of the lecture. Basically, what we did is we gone through derivative and integrals for a vector function. Okay. As we noticed, derivative integrals of vector function are very much similar to derivative integrals of a scalar function, except now we're dealing with the vectors. Okay. So in this question, it looks a very simple vector function. So t squared 3t 5t, and we want to obtain the unit tangent vector, unit normal vector. Okay. So in order to obtain the unit tangent vector, we have to obtain the tangent vector, which is just simply the derivative of this vector function. Sometimes we call it velocity. Okay. And then you normalize this result here, and we get the unit tangent vector. Now, to obtain the unit normal vector, the formula-wise, basically n hat is equal to dt hat over dt over dt hat over dt's norm. So apparently we need to obtain the derivative of this unit tangent vector first. So that's how we stopped it here in the previous lecture. So here is your unit tangent vector, and then I need to obtain the derivative of this vector function. A derivative of this vector function basically means you take a derivative of each one of the components of this vector function. Now this is where I have cautioned you guys. Basically, if this is the time to pick up your first year derivative, refresh your mind and refresh your knowledge. To look at this one here, this is the time. You can use either quotient rule or product rule to solve this kind of a question. For quotient rule, okay, remember the formula, okay, firmly. So this is the quotient rule here. So we treat the numerator and the denominator, one as u and the other as v. Okay. So I'll use quotient rule for this example right here, okay? And I'll calculate the derivative for the first term first. Okay. So we're talking about derivative of the first term. So remember, in this case here, my u is 2t and v is square root 4t squared plus 9. And often in time for square root or root, okay, you can write it in the powers format. Okay. So that's to the power 1 over 2. So now I'm ready to apply the quotient rule at here. The bottom here is v squared, so v squared that becomes 4t squared plus 9. And top here, first calculate the derivative of u. So first calculate the derivative of u here, which is 2, right? Derivative of u is 2. And then times v, so you don't change the v at here, and you can just simply substitute v back here. And then v prime. Okay, so v prime is derivative of this term. So I'll just take the derivative, this one here. So we're talking about derivative of 4t squared plus 9. Okay, so for this one here, this derivative. This one here actually involves a simple chain rule at here. So you can temporarily say, okay, let w equal to 4t squared plus 9. Okay, so and then this becomes just dw. So this basically becomes the derivative. What's the derivative? W to the power of 1 over 2 now, right? Yeah. So you can see this is d this over dw first, and then dw over dt. Okay, so that's a simple chain rule. And w to the power 1 over 2's derivative is 1 over 2w, and then what? 1 over 2 minus 1, which is negative 1 over 2. And dw over dt is the derivative of this one here over t. That's 8t. Right, that's 8t. So put the w back over here. Okay. So it does involve a simple chain rule, right? When you're getting become more familiar or become more proficient, you don't have to every time write down this chain rule. So I'm going to put these results back into the numerator at here. So that gives me 1/2 at here, 4t squared plus 9, negative 1/2 times 8t. Okay. So that's pretty much the results of this derivative. Okay. However, okay, you don't stop at here. Okay. You have to simplify it. If you don't simplify it, and if any other derivative, any other operation is required, this is too much of a computation for the rest of the calculations. So we have to simplify it. To simplify, this is actually what I find for some students also having trouble to simplify these kind of things at here. This is actually pretty straightforward because this is 4t squared plus 9 to the power of a negative 1 over 2. Okay. So let's simplify this a little bit here. So 1 over 2 times 8t give us 4t, and this is basically 1 over 4t squared plus 9, 1 over 2. So I'm not skipping any steps at here, just for the benefit of any of you having doubt where this is from, right, where the results is from. So that 1 or negative 1 over 2 become this. Okay, so then you simplify the fraction now. Okay. So 2 times 4t squared plus 9, 1 over 2 times this, and minus 4t. And at the same time, the denominator, and also times that 4t squared plus 9, 1 over 2. Okay? Yes?
I think you wrote 2t when you did your portion rule. You didn't multiply by t again. You use that 2t.
Which step?
Yeah, right in there you got 2t, like your t.
Oh, I did it. Yes, you're right. Yeah, I have a 2t here, of course. Excellent. Yeah. That's the kind of mistake you could make. So, I guess now I have, this is instead of 4t, this is becoming 8t squared, isn't it, right? And now this is 8t squared. Okay. Excellent. So the square times the square root times the square roots, and that gives you just simply 2 times 4t squared plus 9, then minus 8t squared. Here, use the power rule, so 1 plus 1/2, which gives you 4t squared plus 9, 3 over 2, right, to the power 3 over 2. So now you can see the numerator, right, happen to have a 8t squared, and you get 18 over 4t squared plus 9, 3 over 2. Okay. So without skipping any step at all, this is basically all the details involved in calculating this derivative at here. Okay. Any questions? Okay. So if you're having any doubts at here, then I strongly encourage you to practice this kind of derivative. Even though some of the concepts you understand completely, but if you're stuck on the computation, you could still get into trouble, right? Okay, so now this is the derivative of the first term, and similarly you can calculate the derivative of the second term at here. So you can get the derivative of the second term. So similarly, you get negative 12t over 4t squared plus 9 to the power of 3 over 2. So that's the results of the derivative. So then you can put it together. You get dt hat over dt, which is equal to 18. Now, because if you look at these two terms, both of them have this 4t squared plus 9 to the power of 3 over 2 as a common factor, right? So I'm going to just pull it out. And then you have 18 minus 18 and then negative 12t, okay, as a vector. Okay, that's your derivative dt hat over dt. Because the next step we're going to calculate the norm, the length of this vector. So I can still do one more step. I'm going to take another common factor out of this 18 and a negative 12 at here. 18, 12 has a common factor of 6. So I'll put a 6 over here. And this is to become 3 and a negative 2. The reason I'm doing this is basically when I calculate the next step, the length of this vector. Okay. Whenever you have a common factor, this is basically the scale, right? The scale here. So that scale may remain as a scale for the lengths. Okay. And then you calculate the rest of the length of the 3 and negative 2t, which is 9 plus 4t squared. So that simplifies your calculation. So when you calculate the length of the vector, you should try to pull out the common factors first, and then just calculate the length of the rest vector here. Okay. So the good thing is now we can do a little more simplification now, because both the numerator and denominator has this 4t squared plus 9 at here. And this is 4t squared plus 9 to the power of 1 over 2. And if you simplify this, you get 6 over 4t squared plus 9. So finally, we can put things together. Putting things together meaning we try to calculate the n hat over that particular norm. So this whole thing over this whole thing. Calculate carefully, you'll get that's your n hat. So unit normal vector. So I'll leave one of the exercise for you to do. What is the binomial vector? So if you recall that giving any curve, okay, so giving any curve, right, you can always calculate the t hat, you can always calculate the n hat, and then if you use the t cross n, you'll get the b hat, which is the binomial unit vector. So the t hat, n hat, and the b hat, they are basically 3 unit vectors perpendicular to each other and forming 3 perpendicular normal planes, essentially, right? And this is exactly the kind of idea to define a coordinate system. So when you have a Cartesian coordinate system, you basically have I hat, j hat, and k hat, 3 unit normal vectors. This is a very useful, actually, this system in here is very useful notations. So this is called T&B frame, and there's another name called freenet servette frame. Very useful frame. Especially, I'll give you an example. In robotic application, okay, industrial robots. So one application is, or one desire is, we want any factor of the robot, which is, let's say, the hands, right, to be able to track certain objects. So track certain objects often in our mind means, okay, let's just grab this, right? That's tracking, okay? Yeah. However, there's another layer of tracking here is you also want to use your hand, not just land up at a location, but also land it at a certain orientation. So for example, I want to grab it in this direction, or grab it in this direction, or grab it in that direction. That's what we call the orientation, right? So how do I define that orientation? And basically, how do I define the approach, the direction we're going to grab it? So you define basically at the end of the robot, or the end effector, we call it end effector here, you define a frame which is T&B frame. So attach a frame at the end effector. Attach this kind of frame. For example, I can define the axis, okay, which is perpendicular to the palm of the hands, and let that to be, I don't know, let's say let that to be the n hat direction. And then you can define the t hat and the b hat corresponding. Right, so that's what we call to attach a frame at the end effector location. So then the mathematically, once you do that, then the question about orientation becomes, how do you orient this frame now, right? So how do you orient the frame to be exactly the kind of orientation you want, so to approach the certain objects here, okay? So here's a simple animation in here. I'll show you. Actually not that simple. So this is a Puma robot, the first kind of industrial robot. You probably see 6 degrees freedom. In this case here, I wanted my Puma robot to track a helical curve, which we learned, right? The helix kind of parametric equation. At the same time, you watch that frame attached to the end of the end effector, that's blue, green, and red. Okay, so I wanted my end effector frame to be oriented at any time to be the same as that the T&B frame calculated from a helical curve. So that's the idea. No, not just going along this helical curve, but also there's keep time varying change for the wrist. Okay. So you can later see how that changes at here. Now in this application here, one of the crucial steps is basically first write down the helical curve equation. Let's say I don't know what it is, but for example, maybe this is our helix curve. Then the next step is you have to calculate what is this t hat, what is the n hat, and what is the b hat. So that is your T&B frame at any point along that helical curve. And then to align the end effectors, the robots, to be the same as the t hat, n hat, b hat as this one here. Right. So they see the calculation of the t hat, n hat, b hat. It's a crucial part of the simulation, right, which I demonstrated to you. Okay. So that is one application in here. Okay. Before we end up this part of the lecture, there's one more example I wanted to show you, which is also kind of related to one of the assignment questions in here. Okay. All right, so here is a parametric equation given. Now this one here, it's not a kind of parametric equation like the other examples, okay? Because it's all symbols first of all. Okay? There's no specific values for theta right here, right? So there are 3 theta t, but it's still a parametric equation. So r ultimately is a function of t, but superficially r is a function of theta first. Right? So r is a function of theta, and theta is function t. So ultimately r is a function of t. Okay. Now if you plot this thing out, you actually end up with a fairly interesting curve. Okay, what we call is a roller coaster curve, okay, trajectory. If you go to an amusement park, you'll see, the roller coaster actually sometimes all the time follows this kind of this type of parametric equations involving sine and cosine. Okay, one of the in the assignments give you another example for roller coaster curve. Okay, so this is the parametric equation or trajectory for the roller coaster, and what we want is we want to know what is the velocity. Okay, if you're traveling in a cart, okay, along the roller coaster, what's the experience of velocity at each location? Okay. So that's very easy. Just take derivative of this dr over dt. Okay. Now, technically speaking, what you do at here, you need to use the chain rule. Okay. You need to use the chain rule to calculate. So dr over d theta first, and then d theta over dt. Now, I'll calculate dr over d theta first. Now, d theta over dt, because the question didn't give you anything about the theta, so we'll keep the d theta over dt. This is what normally we call a symbolic calculation, so we'll keep the d theta over dt here. So let's calculate what's dr over d theta, which is the first derivative here, so it gives us cosine theta, and then times d theta over dt. I'll just use the theta dot. Okay, that's a Newton's notation. If t is the time meaning, then d theta over dt can be represented using theta dot and I hat, plus the second term, the derivative, which is 2 cosine 2 theta, and then times theta dot j hat. Last one is negative sine theta dot and k hat. Okay. So basically, if this question is all we have, then you end up with here. That's it. That's the velocity profile for the given roller coaster. Okay. Okay? Yeah. Now, the only thing I find in the past is some student confusion is what do I do with the theta dot? You leave it because we don't know what the theta is at here. However, okay, if you do know what the theta is, for example, right, if theta happened to be just omega t, okay, then this particular derivative can be further calculated now, because theta dot is the derivative of theta over t, and then times omega. So that's for one more step. And I think I'm supposed to substitute the theta back into this equation in here. Okay. Yeah. So that's the difference between whether you know theta or you don't know theta. Okay. Just be careful. This is omega is not part of the cosine or sine. Okay. Okay. So you can apply this example to the assignment question, okay, which is similar type of question. So derivative integrals of a vector function, really it's just involving derivative integrals of a scalar function, because you're literally taking derivatives or integrals of in the component of that vector function. Okay, so not much difference. Okay. Any questions so far? All good? Okay. So let's continue now to a different concept now. It's a new concept, which of course involves this vector function. So the first I wanted to talk about is how to calculate an arc length. And then from arc length, we'll look at another concept called scalar line integral. Okay, so first of all, what do we mean by arc length? Okay. So I'll draw something to illustrate the idea here. Let's say I have a curve C given in the 3D space. And the curve C, let's say starting from t equal to t1 and end up at the t equal to t2. And it has a parametric equation R of t. So what I'm interested is, what will be the total arc length for this curve C from t equal to t1 to t equal to t2. It's a curvature curve, okay, and you don't have the luxury to just straighten it out and then measure it. Okay. And how do we calculate this mathematically? Basically, the total length of this curve C, which is called the arc length. All right. Yeah. So this is objective here, to find the length of curve C, right, from t equal to t1 to t equal to t2. So let's see how we can approach this question in here. So I'm gonna just draw. First of all, let's draw some arbitrary vectors along the curve C here. So let's say I have 2 points, okay, along the curve C, A and B. Then I will be able to construct 2 vectors, 2 position vectors. That's 2 position vectors representing point A and point B. Let's denote it as R of A at here. Let's see. Let's denote it like this. So let's say this is at the t equal to ta. This is t at the t equal to tb. So at that 2 particular time moment, you are at location A and location B. Then for the position vector B, you have a parametric equation R at TB moment. And here you have R at TA moment. Okay, so that's the notation wise. And then I will construct a vector between A and B. So let's construct a vector between A and B. Okay. That's it. Okay. So now let's use the idea of approximation, basically the idea of limit, to obtain the arc length. So first of all, okay, let's calculate what is the vector between A and B. So let's call that delta R here. Okay, let's call it delta R. So that's the vector between A and B. And it's quite straightforward. Okay. First of all, let's get rid of the absolute sign first. Okay. What's the vector between A and B? you have this triangle here, so that's the vector vector OB minus the vector OA, right? So that's R at TB minus the R at TA, which give me the vector AB, which is delta R vector. Okay. And now I will calculate the length now. Okay, I'll calculate the length. So give me the length of delta R vector, or the length between A and B. Good? Okay. Now remember, we're trying to obtain is the arc length, the curve C. Then the portion of curve between A and B is not a straight line, right? It's a curve. So if I let delta S, okay, as the arc length between A and B, so let's let the delta S to be the arc length between A and B. If I want to use approximation methods, then the closest approximation to the delta S must be what? What will be the closest approximation for the arc length delta S set here? Is approximately equal to? Exactly. Okay. The closer A and B's are to each other, then the better approximation you have between the delta S and delta R. That makes sense, right? Yeah. Okay, so let's work on this from this line here now. So I find myself a way of approximating it. And delta R here, so let me rewrite. Actually, I don't need to rewrite it. So such delta R right here. Now I'm going to make use of knowledge that we reviewed, if you recall that. What is the results of a vector dotting itself, which give me exactly, right? That's the thing we learned in previous lecture. So now if I look at this normative here, I can write down an alternative for this length delta R, and basically I'll write it as a delta R dot itself and take square root, right, to give me the length. So that's your delta S is approximately equal to this. Furthermore here, okay, I'll make a little more approximation. I'll divide each one of the term, okay, this is dot product. I'll divide each one of the term with a delta T. So basically, the traveling time from TA to TB, I'll call it delta T. So that's how much time it takes to go from A to B. So divide delta T here. But I can't just divide delta T, because basically I cannot alter this expression here, right? So I have still to keep it exactly the same as this expression. Then what do? In order to keep it the same, the whole thing at here I need to multiply with exactly, right, delta T. So this way we're keeping everything the same, and but now we have a delta R over delta T now. Okay, yeah, good. So back to this approximation, right? Back to the approximation here. We said it's approximation. Why? Because A and B here is actually a straight line, but we're talking about it's a curve at here. However, we know that if TB is infinitesimally close to TA, then this delta S and delta R will not be approximation anymore. Will actually become the same, right? That's the idea of a limit, the calculus. So if you let TB approach to TA, or if you let basically delta T goes to what? Go to 0, Okay? Then this delta S and delta R will become the same. But we don't use the delta anymore. For that kind of infinitesimal idea, the delta becomes straight D, right? Straight D is an infinitesimal small quantity. Yeah. So the delta becomes straight D. And then square root all of the delta, okay? All of the delta will become straight D. So now this comes nicely actually as this differential form. Right? This is what I call as the differential format. Infinitesimal small segment ds, which is basically what we call the differential form. And then from here back to the objective, which is to compute the arc length of the curve C. And S at here representing is basically the variable of arc length, right? So in your first year calculus, if you should remember, integral of a d anything give you back what? Give you back the anything, basically. Right? Integral of d anything, if there's just one here, give you back this whatever inside the bracket. In this case here, integral of the arc length, the whole arc length from beginning to the end, should give me back this total arc length. Okay, so this is basically you're doing like additions. I'm gonna add up all the differential infinitesimal small arc lengths together, right, using the integral concept, and that gives me the total arc length. Okay, yeah. So this is the final format for calculating the arc length of a given curve C. And of course I need to write down the limits for the integral, because we're talking about the t limits here. So the t goes from t1 to t goes to t2. That's basically the beginning value of the t and the end value of the t for that segment of our curve C. Very useful expression. A very useful expression. You can actually, I don't have time to do this, but I want you to encourage you to review, as a matter of fact, the arc length. So, for example, if in a 2D space, if you're given a scalar function f of x, and you're interested to know basically what is the arc length for that particular function or curve within x equal to b and x equal to a. There is a formula for that, which is s equal to a to b 1 plus dy over dx and dx. Okay. This is becoming actually a special case of what we just derived. So it's quite simple. If you let x to be the parameter t, you basically will get back to this general function and general results at here. Okay, so there's a connection between these two. Okay. Yeah. Okay. So in terms of formula, if you had to remember for midterm, this is, let's call it, this is one formula. Particularly, this is formula coming from here. Okay, your ds, which is the small segment of the arc length. Okay, so these two, if you have to remember, just write down a couple times on the piece of paper, and you'll be able to remember it. Okay. Yeah. All right. So let's see the examples here. Okay. Given R of t parametric equation at here, and the corresponding t's range from 0 to pi, and I want to find the arc length. Okay, before we jump into this, okay, so let's take a look at this given curve. RT is cosine 2t sine 2t, and the t's go from 0 to pi. Can you tell me what kind of a curve this R of t represents? Circle, right? It's a circle. And 2t sine t, how much of a circle? Is it 1 turn, or 2 turn, or half turn, based on the given t's range? 1 turn, right? So 0 to pi, if you plug in 0 here, start at 0, plug pi here, and a 2 pi. So it's just 1 turn. Or essentially, if you plot it out, you get just a circle, right? Going from beginning till the end. So 1 turn. And asking for arc length. And circle has a radius 1. So honestly, do we need to calculate? Right? We don't, right? 2 pi r. That's the circumference. However, I still wanted to calculate this, right? Let's corroborate. So let's just verify if the result is 2 pi r or 2 pi in this case. Okay. So I'm going to verify that using the formulas that we just derived at here. Okay. So let's do that. So this formula involves dr over dt. So we need to calculate the derivative r over dt first. So let's do that. So let's do what's dr over dt. You have a 2D curve, so you save yourself z over t, of course. Derivative of dr over dt basically means derivative of each one of the components at here. So that gives me negative 2 sine t, negative 2 sine 2t plus 2 cosine 2t for the derivative. And then coming back to the formula, I need to do the dot product for the dr over dt to itself. So let's calculate the dot product. And dot product, as we learned, when you dot each self, it's basically the squared of the length. So let's see what that b is. So you have the square of the first term plus the square of the second term. So the square of the first term, the square of the second term. Okay. Now this is the least kind of a formula, trigonometry formula I would expect you to remember. What's cosine theta square plus sine theta square? 1. Okay. Yeah. Now a lot of people actually worry about formulas in the exam. I typically won't trouble you with very sophisticated trigonometries, but this is the only one I would expect you to remember. Okay? Yeah. If there's anything else, like of course you need to know, what the tangent theta, cosine theta, right? Sine theta relationship. Okay. In the final exam, you'll get a formula sheet with the very common trigonometry formulas. Okay. But in midterm, you won't have the formula sheet. Okay, so let's get back to the formula for the arc length now. So arc length S equal to integral. In this case, t goes from 0 to pi, and then square root dr over dt dot dr over dt here, and 0 to pi here. So we calculate the square root already, so that's square root 4 times dt to 2 pi. Exactly what we're looking for. Another thing I also want to emphasize is I know a lot of you have your own habit of writing in terms of mathematical expressions. Okay, I really want to normalize this whole thing out here. And every year I would emphasize, when you write down an integral, don't forget to write down this. Okay? Because I've seen so many students, when they write the integral here, for example, x squared, that's it. Right? And what are you integrating with? Right? Especially now we're dealing with multivariable calculus later, and you have more than just one single variable. You need to basically write down what are you integrating with, okay, to finish this integral. Okay, good. So that's the arc length at here. Okay, that's the arc length. Now let's take a look at one more simple example, and then we can move on to the next topic. Any questions so far? Yes.
When we dot products to ETs, do we not need to worry about I and j components after that?
Do we worry about the IJK, you mean?
Yeah.
Oh, yeah. Dot product give you what kind of quantity? Scalar, right? Yeah. So you don't need to worry about the IJK anymore. But cross product give you vector. Okay? Yeah. Good. So let's take a look at a different. Let's look at a different parametric equation. So cosine t, sine t, and t. This is a helical curve, a helix. We wanted to know. Let's just suppose you have a glider, right, or a spider moving along this helical curve. So it started here. So I wanted to actually calculate the arc length goes from 0 to 2 pi. Okay, so 0 to 2 pi, that's basically starting at here and end at here, right? And what will be the arc length, okay, or the traveled distance if you go up by just one turn, 0 to 2 pi. Okay, so arc length equal to what? So very similar calculations involved in this question and here. Okay, just a different parametric equation. You still need to calculate dr over dt. So at this stage, I encourage you to write down all the detailed steps first. Okay? And you can skip a few steps if you want once you get familiar. And then you can calculate dr over dt dot itself. In this case here, sine t squared plus cosine t squared and plus 1 at here. Okay. Again, the trigonometry here, which is 2. So arc length S equal to 0 to 2 pi square root, right, dr over dt dot dr over dt, and then dt at here, and that's square root of 2 times dt, 2 pi times root 2. Okay. So okay, yeah. Simple example, arc length. Okay, so now let's take a look at the next one here, okay? Scalar line integral. Scalar line integral. So let me lay down the question first. You know, basically, what kind of application we're looking for, or we are looking at for this so-called scalar line integral. I'll start with a very simple application which you have actually learned in the first year. Okay, so let's say I have a piece of wire, okay, given here. So here's a piece of wire. I'm going to put this wire, let's see, okay, put it's a straight wire to the x-axis. So suppose a start at A and end at a B location. Okay. And then this wire has a density rho x. Okay. And I'm interested in what is the total mass of this piece of wire. How do I calculate the mass of the wire here? So I'll show you quickly the steps that you have learned in the first year, right? How do we calculate the mass is, here's what we can do. I'm gonna pick a small mass anywhere between A and B. So suppose you picked a small mass at an xk location. So you have a delta mk at this location. So very small segment at xk x equal to xk location. I can calculate the small mass delta mk. Because it's a small segment we have selected, then we can assume that the density at that location, okay, or within the small segment, remains constant, which is rho of x over k. That's the density. And then the density times the small segment delta xk. So these small segments at here, the length delta xk, let's call it. So that's you can obtain the small mass right around that location. Then if I need to know the total mass, okay, I need to know the total mass, then the total mass can be approximated, right, by adding up all of the masses of all of the small segments. How many? Let's say if we separate it into, I don't know, n number of them, for example, right? If there are n number of these small masses here, then I will just simply add them all up. Okay. Will give me an approximated total mass for that piece of wire. And that's a sound approximation approach. But we do need is a accurate calculation or number. Then what do we do? So to make it more accurate, we let the number of segments of the small mass go to infinite. Right? Go to infinite. If that goes to infinite, then you have an exact mass calculation of this piece of wire. So the connection between the summation sign and integral sign is when n goes into infinite, then the summation sign basically becomes integral sign. Right? So the summation becomes integral, and you're integrating from A to B now. The rho will just become x. As n goes to infinite, the delta x, the delta sign, goes to straight d, right, to the differential. So that becomes dx. So that gives you the total mass, which is an accurate calculation, precise calculation. Clear? Right? That's quickly review of what we learned in the first year, how to use the calculus, right, to get the total mass. So now we have a similar problem in 3D now. Okay. So we can have a similar problem in 3D. So let's say I have a curve C given. So given C as R of t, and also given is the density of this curve C. So density, if you look at this one here, right? If you look at this one here, the density here is rho of x, because in 3D, it's in 2D, so you have just for any x here, you plug in the x, you get the density. But in this case here, if you pick up any point on the curve C, the coordinate is what? X, Y, Z, right? It's X, Y, Z. If I wanted to know the density of that location, so the density function needs to be f of x, y, z. So you plug in the actual location x, y, z to that function, density function. Then you get a density at the location. So this is the difference, right? This is the first difference that here. Okay. Then I would have a similar objective now. What is the total mass for this particular curve C then? Right. So let's say the curve C goes from t equal to A to t equal to B. Okay, so starting at here and finish over here. Okay, so I'm going to use very similar approach as I illustrated for the simple piece of wire right here. Okay, to do the calculation. I'm going to pick a point, okay, any point on the curve C. So let's call it x of k, y of k, z of k. So that's a general location between the starting at end point. And then I will pick a small segment of curve or arc length around that location. So I will call it delta s k, okay, small segment around that location. Then the calculation of the mass. So let's start with the calculation of the mass of that small segment. Okay, so delta m, okay, delta m equal to what? Let's call it delta mk equal to basically the density at that location. Because it's small, then I can assume the density won't change within this small segment times the arc length of the small segment. Density times the arc length gave me the small mass. So if this is only the mass for only one small segment, if I want to know the total mass, I could use an approximation idea. I can add up all of the masses of the small segment, and suppose that I have n number of them. Right, I have n number of them. Yeah, exactly the same kind of idea, isn't it? Right? Same idea. And now I wanted to have the accurate calculation. So now I'm gonna let my n go to infinite. Once n goes to infinite, then the total mass, okay, will become precisely, and the summation now becomes integral sign. The delta become straight d, differential symbol, and then here is you're integrating along the curve C. Now this is basically a formula of a so-called scalar line integral. Okay? Yeah. So basically, let me repeat the meaning of the integral right here. You're integrating this function f over the curve C. As simple as that. So mathematically, what it means is, so basically integrating f of x, y, z over this curve C. That's essentially what it means. Just like the piece of wire formula here, you're integrating this function rho. You're integrating this function rho over the range, the wire, which is between A and B here. Okay. Except right now the function we're integrating is a function of 3 variables. That make sense? Yeah. not much difference. So what about the 2D case, right? Let's think about a 2D case. If you have a 2D case, basically, let's say if I have a piece of wire within xy plane, okay, within xy plane, r of t. So in this case here, because it's a 2D, then the r of t will only contain x of t, y of t now. Okay. If it's a 2D, right? So this is in 2D here. Similarly, right? You will be given r of t and the density function, okay, or let's just call it function now. Right? Instead of function 2 variable now, you have a function with instead of function 3 variable. Now you have function 2 variables, f of x, y. Okay. So picking up any point x, y here, you have a density or a certain function value defined at that location. Then the line integral basically become integrating, okay, f of x, y over this curve C. So in terms of formula, you have basically two kind of formula to deal with. One is a curve C in a 3D space, another is a curve C in a 2D space. Okay? Yeah. So how do I calculate this line integral, right? Seemingly we don't have anywhere to start with, but we actually start, let's say, with a ds. So what is the ds then? As we just learned, ds that here representing as a differential form. It's an infinitesimal small arc length. The formula we just learned. What is the ds? dr over dt, then dr over dt times dt, right? That is the ds formula we have just derived. So I'm going to replace the ds, okay, into the scalar line integral formula here. Okay, replace it into this ds and ds at here. Okay, so then the scalar line integral becomes. I'll keep the f bracket because I'm going to fill out the s here. But now ds becomes this. Okay, ds becomes this. So how do I deal with this given density function or given function f at here? How do I deal with the f? Now remember the sentence I wrote down here. The integral we're dealing with, okay, the scalar line integral is you're integrating this function over c, which basically means what? Means the x, y, z, or x and y here, okay, they're not x, y arbitrarily anywhere in a 3D space. They are x, y, or x, y, z at which location? At C, on the C here. So they're constrained on the curve C because you're integrating along the curve C. So you're only talking about the x, y, z, or x, y along the curve C here. Okay? So, yes? It does, yeah. You need to have a limit like this one here, so t equal to a at here and t equal to b at here, right? Yeah, you need a limit basically. Okay, so x, y, z, or the x, y here, they are not arbitrary coordinates in the 3D space. They are coordinates on the curve C, which is given by which one? By the parametric equation, right? Then in terms of the x, y, z here, I need to substitute the x, y, z with the parametric equations x of t, y of t, and z of t. To finish this integral, you need a limit. And that's what Felix pointed out. So you need t to start and t end value. Okay. So whatever the starting value and end value. And that depends on the parametric equation for the curve C. That make sense? Now this is essentially more or less the finalized formula now for scalar line integral. So I'm going to write down the 2D case too. So you have essentially two formulas to deal with. Okay, the first one basically includes the second one. Okay. Is that good? Okay. So I'll show you a couple examples, and then you'll see how it is done. Okay. This is actually not too bad in terms of calculation. Okay, here's curve C in 3D space. So it's basically a straight line, starting from origin and end up at 1, 1, 1. Okay, so let's call this C here. And I have a function x, y, z. Okay, so defined as so here's function, and if you plug in any point on the curve C into the function, you'll get back a certain value returned, right? So that can be the density. So now I think I should emphasize, because I started with density, but the mathematical doesn't have to be density, right? Mathematics can simply mathematical function defined over this curve C here, and I want to calculate what's the line integral of this function over the curve C. Okay, so for this kind of question, so from now on, you probably will be given the parametric equation, or you probably don't have the parametric equation in the question. Then you have to basically write down the parameterization of this curve C first, okay, before you can proceed. This is kind of straightforward because it goes from 0 to 1, 1, 1. So basically, x goes from 0 to 1, y goes from 0 to 1, and z goes to 0 to 1. Right? Then a possible candidate parametric equation for the curve C could be what? What would be a possible candidate of the parametric equation for the curve C? Exactly, right? TTT. Now, once you lay down the TTT, you also have to put down the range for the T. Basically, where did it start and what value does it end, right, for this parametric equation? 0 to 1. 0 to 1. As I said, some students may choose a different parametric equation. You may choose 2T, 2T, 2T. Then your T will go from 0 to 1/2, right? Because that's crucial, because your value, the range of the T decides on the calculation. Now, for f of x, y, z here, okay, and if I look going back to my formula at here, okay, I need the dr over dt. I also need to substitute the parametric equation of the C into the function f. So let's do these steps here. Let's calculate dr over dt first. And this is very straightforward, 1, 1, 1. And next, I will calculate what will be the value, what will be the function f of x, y once I substitute the parametric equation into this function f. Now this is where I have found troubles in the past. Students having trouble doing the substitution for x, y, z into the function f. So here is your x of t, y of t, and z of t. Substitution basically means you put this x of t into x at here, putting the y into the y at here, and putting the z of t into the z at here. So that's how you do doing the substitution. As you can see, when you substitute t at here, 3t squared, and then plus t at here. Okay. That's called substitution. So this end up with a 2t minus 3t squared. Good? So then let's put everything back into the formula. So into this formula here, okay, into this formula. So the line integral. So I'll put down the limits at the end. Okay. First, this is your f function here, which is 2t minus 3t squared, and then you have your dr over dt dot dr over dt, and then dt. The integral limits here is 0 to 1. Okay, 0 to 1. Okay, so 0 to 1, 2t minus 3t squared, and dr over dt dot itself is 1 plus 1 plus 1, so that's root 3. And then the rest of them becomes a calculation of an integral of a single variable now. So that's actually pretty straightforward. So this root 3 is a constant. You can take it outside here. 2t is t squared t cubed, and it goes from 0 to 1 for the limit. Overall, you end up with 0 for this integral. Okay. Yeah. I do get questions in the past, a student, what does 0 mean, right? Does that mean you have a weight of mass of 0 for this second wire? Sure, yeah. If you think of this as a density at here, then you end up with a 0 weight. But mostly this is purely mathematical calculation. Okay, so that just basically means the scalar line integral for this particular question end up with 0. Okay? Physically, probably not possible to get a 0 weight, right? Okay, so let's look at a slightly different version of this question, which we're running out of time, of course. Okay, but I want to get started. Okay, just okay. Now, previously, our curve C goes from origin to here. Now this time, I'm going to ask you to do slightly different route. To go to 1, 1, 1, this time, let's go from 0 to 1, 1, 0 first, and then from 1, 1, 0 to 1, 1, 1. Okay, so that's different route, but at the same location. And we're going to use the same function f(x,y,z). Okay. And I wanted to integrate, so this time, so I will remove the c here. Okay, so this time you see this curve c. Okay, this is curve c. Literally is actually what? It's c1 plus c2. Right, it's c1 plus c2. So if I need to calculate this scalar line integral, so in essence we're doing is integrating over c1 plus c2. So that's what we're doing. Now back to your first year, if you recall that when you do integration, there is a concept called what? Piecewise integral, right? So you can separate the integral into pieces if you're dealing with the pieces. So here you have exactly the same kind of idea. You can integrate this using this so-called piecewise integral. Okay, there are only two pieces, so we just have two pieces of integration here. From here, right, you deal with each one of the term, And you actually use essentially exactly the same strategy now. First, come up with a parametric equation for C1, C2, and then deal with each one of the terms separately. Is that okay? Yes?
Why you integral f x y z over f, like ds instead of d?
Right. So this is this is the initial derivation of the scalar line integral here, right? You can always replace the ds with the formula for the ds. But this is actually what happens next. So we're going to replace ds with, this is the first segment. And then you have the dt over here. Right? Yeah. Okay? So I'll finish the example in the next lecture. Any questions? All right, good. Thank you.